This example is about the Toluca company. We'll be revisiting this data set from time to time. It is used quite a bit in your book, Applied Linear Statistical Models by Kuttner et al. And you can read about this example or about the Toluca company in chapter 1. I'll just read a little bit about it from your book here. It says that the Toluca company manufactures some refrigeration equipment as well as many replacement parts, and in the past one of these replacement parts has been produced periodically in lots of varying sizes. Now, when a cost improvement program was undertaken, company officials wanted to determine the optimum lot size for producing this part. See, if you've ever worked in a manufacturing facility, you'll know that every time you set up a run or set up a lot of things to produce off of a machine, there's some setup cost involved. Oftentimes it takes a setup man or woman to come and set up the machine before you can begin producing that. So so this production of this part involves setting up the production process, which must be done no matter what the lot size is. So that may be some constant cost. And then machining and assembly operations. Maybe these things are linear in the lot size or something. So one key input for the model to ascertain the optimum lot size was the relationship between lot size and labor hours required to produce the lot. So that's what this data set is about. What we're interested in examining here is the number of hours required to produce a lot for a certain lot size. Okay, so I'm just going to go ahead and drop these, pull up this data set. I'm just copying. I know you can't see everything there, but this is all from the notes that you have. If I type head data now, I should see this data set. Notice that I've renamed the variables here. I've got lot size here, and in the first column, and work hours over here in the right-hand column. Okay. Now I'll go ahead and make a scatter plot, okay, of lot size versus work hours, and put my appropriate labels there, and it looks like that. Okay, so you can see that there's a positive linear trend there, right? As lot size increases, the number of work hours tends to increase. So now I'll go ahead and do some linear regression there. Build a linear regression model, and maybe I'll plop a line down on the scatter plot. I'll even color it red or blue. I like blue. Okay. And if you go back to the window there, you see there's the nice regression line. And if I do summary of out, okay, out is what I call the output oftentimes for my running a linear model. Reminds me what I did up here, okay, that we did a linear model of this form, data from column 2 versus data on column 1. And here's some basic statistics on our residuals. Remember, the residuals are just the observed error values off the line. So if I look here, you know, the residual corresponding to this point, remember, is just the distance it is off the line and in what direction, in the y direction. Okay, so it would be positive, looks like, I don't know, positive 110 or something like that from here to there. This one is probably more like positive 40. Okay, this residual corresponding to this point, of course, would be negative, probably negative 40, negative 42, something like that. Now I'm going to also, of course, you effectively have the regression line equation here. This number is your vertical intercept. This says that essentially if you have a lot size of 0, then you're spending 62 work hours. Okay, lot size of 0, 62 work hours. That's what the vertical intercept is. And remember, maybe this corresponds to that setup cost, right? So that even if you don't manufacture anything, this is how much it costs you perhaps to set up the machine. And then this is your slope estimate. Okay, this is B1, which is your beta 1 hat. It's the estimate for the true slope for the true distributional point pattern. Okay, so And this indicates that for every one unit of lot size increase, the number of work hours seems to increase by 3.57. Okay. Over here, skip all this stuff. This stuff just leads to these t-tests, but these are the p-values for the t-test for these two estimates. And remember, the null hypothesis in each case is that these coefficients are equal to 0. So this is essentially saying that, you know, at like the 2.5 or 3% significance level, there's sufficient statistical evidence to conclude that the intercept is not 0. And at a much more significant level, or a much smaller level of significance, but with carrying with it a higher level of significance, the slope is very likely not 0, is what this is saying. 10 to the negative 10th. That's pretty darn small. This is like what, half of a billion, half of 1 in a billion or something. Okay. These are just some significance codes. 3 means really significant. Okay. 1 means not as significant as 3. Anyway, just look at the numbers. And here's your R-squared value, 0.82. That's pretty high. And again, here's your F statistic if you want to look at it that way, in terms of looking at this with regard to regression. This is the same test right here. This p-value is from the same exact test as you're doing right here. Okay, they've just rounded differently down here for some reason. Okay, remember that an f random variable is the same as is the square of a t random variable. Okay, t random variable with d degrees of freedom is an f random variable with 1 numerator degrees of freedom and d denominator degrees of freedom. So it's just, and then I think the only thing here that we haven't really talked about is this adjusted R-squared value, and we'll get to that later on in the course. But so all of this should look pretty familiar. Now what I'm going to do is I'm going to get my residuals. Okay, that's just the next line in the code. I can do that like this. Of course, the residuals are the actual y values of the data set minus the fits, and I can quickly extract the fits from my output of the linear regression just by doing out $fit. Okay, and then I can just type head residuals and you'll see the first few residuals. Another way to do that, in fact, and I'll just call it res because that's shorter is better, is also in your output of the linear regression function, you can just you can type out $residual. There's a column of residuals there in that output. It may be hidden from you. You know, when you type summary of out, it just gives you some of the output there. Okay, but if I do that, you'll see that in fact you get the same thing. Okay, so this is probably a quicker way. I mean, you don't have to think about this formula all the time. If you just want to quickly get the residuals, you can just type whatever you stored your linear model output as $residual, and boom, they'll come out. Now I want to make sure that I hang on to that plot because I love it so much, and so I'm going to type the Windows command. Remember, if you're using a PC, you use the Windows parenthesis command. If you're using a Mac, you use the Quartz command, QUARTZ, I think, with the parenthesis. That'll open up a new window so that you can, hang on to your old graphs. Otherwise, it'll write over the graph in the graph window. So I want to plot my residuals here. Remember, what we're going to do a lot in this section is we're going to check out the behavior of the residuals. Here I'm going to plot the residuals versus the lot sizes. Okay, and so I'll take a look at that. I want to check for several things. I want to check for constant variance, right? If these were fanning out in a way, like if they were sort of clustered down here and then they sort of fanned out this way and that way, then that would be a problem for us. But my eyeball is not really detecting that kind of behavior so much. And also we want to check for normality and independence if we can. Okay, so but that's a quick way to sort of eyeball your residuals versus the lot size. Okay, And you know, one thing I could do is I could write AB line A equals 0, B equals 0, and take a look at this. I've just dropped a horizontal line running through this way. You can think of this, if you like, as this is your regression line, okay? But it's been dropped down. If I grab a hold of the regression line here and just pull it down so it's horizontal, and you know, this is the point pattern. If these data points in the y direction followed this line, came down with it, okay, this is what would happen. So this is a different and kind of easier on the eye kind of view to check out the behavior of the residuals. Okay. Alrighty. So let's get another window, and this time I want to check out standardized residuals. Maybe I want to standardize the residuals. Okay, so I can do that by just taking the residuals and dividing by their standard deviation, and then plot the standardized residuals versus the data. And I should see basically exactly the same point pattern as I saw before. Right? This is my new one. This is my old one. Only thing different is the scaling on the vertical axis, right? Like we talked about, when you standardize variables, the mean is 0 and standard deviation is 1. So that's why this this new vertical axis is adjusted that way. Okay. I'm not even really sure how useful that is, but I guess in terms of standard deviations, maybe that's easy, because then if you see one that's, you know, at 3 or above, you know, more than 3 away, you know, going vertically, then maybe those are potential outliers, and so that can be a good way to determine outliers. Just looking at the plot this way, I'm not really sure what the standard deviation is in this case. Okay, so so that's an advantage to looking at standardized residuals versus lot size. Okay, now let's try this out. I want to create this object called run, and in it I'm going to create a sequence going 1, 2, 3, 4, all the way up to however many rows are in my data, increasing by 1. It's going from 1 to this number, increasing each time by 1. Okay, so you'll see what that is. If you just type run, you'll see it's just 1 to 25, because in fact if you look at the data set, you know, you've got 25 rows. Okay, so that's what run is. And now what I'm going to do is I'm going to bind that stuff to my data. I'm going to put the run numbers in the first column there, and then my data in the next. So actually, if you type head of data now, you'll see that our data set has changed. I've got runs here in the first column, lot sizes here, and work hours here. Okay, and now I'm going to create yet another window, another graph window. And I'm going to plot the residuals versus the runs. Okay, turns out these are the runs in time order. Okay, so if I take a look at that, what am I looking for here? I want to see if there's any kind of a pattern there. Is the run number having any kind of an effect on the residuals? And you know what? I'm not sure. They seem to be sort of tighter in this region. Okay, so that could be a problem. Maybe I could write. I could put lines there. I could connect all those points with lines. Are they? You know, there should be a lot of jumping around, I think, and a lot of the jumps should be. Well, it should look like a bunch of random jumps in some way. You can connect the lines there if you like. I'm going to create another yet another graph. This time I'm going to make a box plot of the residuals. Okay, I'm going to make a box plot of the residuals. All right, and so what I'm doing with this box plot is I'm checking for outliers, and I'm also checking sort of softly for normality. A box plot is not a conclusive way to check for normality, okay? But I know that if the data were truly coming from a normal distribution, I would expect to see, you know, a pretty symmetrical looking box plot, and these ends, these whiskers parts of the box should be a little bit longer than the middle parts, because remember, the closer these bars are together, it means the more densely packed the data values are. The middle 50% of the data fall in the box, right? This is the lowest 25%, this is the highest 25%, this is the, you know, about 25% fall between these two marks, and then the third chunk of 25% falls in here, you know. Okay, so that's not entirely inconsistent with a normal distribution. These are all pretty soft kind of tests, you know, making charts and graphs, but they're fun and they're neat. We love charts and graphs. Let's get a little more sophisticated and make another kind of chart. This is called a QQ plot, or a probability plot. So what I'm doing here is I'm plotting the sample percentiles from my sample based versus theoretical percentiles from a normal distribution, right? So the idea is well, let's say if you plotted the theoreticals versus the theoreticals, then you would see absolutely a straight line going through here. If the idea is, if these numbers are coming from a normal distribution really and truly, then you should see, you know, the lowest one should, you know, sort of line up with your theoretical lowest percentile, and your next one should sort of line up with that next one. You should see sort of a straight line kind of behavior there. And so, yeah, that looks sort of linear. It sort of seems to be a linear behavior there. I could drop a line on that. Okay. Just sort of eyeball that and see how well that fits. Now let's get real sophisticated and run something called a Shapiro-Wilks test. Okay, and you do that by just typing Shapiro.test. You don't need any special package for this. Shapiro.test of the residuals. This will check for normality of the residuals. Okay, it's a hypothesis test where the null hypothesis is that the residuals are coming from a normal distribution, and the alternative is that they're not. Okay, and so it's kind of a sophisticated test, and we won't talk about the details, but the p-value is pretty high. So I would say that there's really insufficient evidence to conclude that the data are not coming from a normal. So we're sort of safe, quasi-safe, I think, in assuming that maybe they're coming from a normal distribution. Another test you can run along the same lines, it's a different test, but it's called the Anderson-Darling test. This test requires the NOR test package. So to get it, actually what you have to do first of all is go up to packages, and you have to install. If you don't already have this package, you have to go to install, and then you'll have to select some mirror. I usually go to somewhere close, USA, Indiana, maybe. Okay, and then you have to look for this package. What's it called? It's called NOR test. I've already got it on mine, so I don't have to install it, but I'll just scroll down here and find it. NOR test. Anyway, it's in here. I know it is. NOR test. Okay, click OK, follow all the directions, and it'll load the package. Okay, well, sorry, it'll install the package. Once it's installed, you will actually have to then load the package, and you can load the package once it's installed by typing library parenthesis and then whatever the package name is, or you can simply click on package and load package and search for it. Okay. So I've loaded this package. It might give you a warning that it was built under some previous version, so you know, in case it doesn't work right or something, but I think this will be okay. And so this is the Anderson-Darling test, AD.test. For some reason, the Shapiro-Wilks test, I guess Shapiro got the shaft here. It's just called Shapiro.test. But Anyway, Anderson Darling AD dot test on the residuals, and I should get a pretty high p-value too. Yeah, okay. So insufficient evidence to conclude that these values are not coming from a normal. So that's good. That's good because we want them to be coming from a normal. That's one of our assumptions that we needed. Let's try something else. Get a new graph window here. And now I'm going to use this command PAR MF row. I don't even know what that stands for, but I know that if I type all this stuff and I put a 2 here, or if I put an I here and a J here, then it won't. Then I'll get a bunch of nonsense. But if I was some number and J was some other number, then I would be the number of rows and J would be the number of columns in my graph window. So it means that I could make, for example, I could make 6 plots on one graph, and the plots would be in 2 rows and in 3 columns. And so, in fact, that's what I'm going to do. I want to make a plot now of I want to make several plots. I'm going to plot work hours versus lot size, okay, and also plot the residuals versus lot size, okay. And maybe then I'll plot, in fact, let's take a look at it. You can see how it's updating it automatically or in time as you're doing it. There they are. Okay. It's pretty neat, right? Then when you type your report, you can just copy all that stuff and drop it into Word or whatever. And I'll make another one here, like so. And I'll put lines on that last one. Okay, I can, and I'll put my box plot there, and see how we're coming there. What do we have? We've got 6 plots there. Maybe I'll do that last one there, the QQ plot, and drop it there. Great. So now what I can do is I can just click here and do Control C, and then when I open up, say a Word document, then I can just Control V and it'll paste it right there into Word. Right? And I can say, here are some amazing graphs, and Control V, right? Bang.